Welcome to the IEEE Future Networks podcast series, Podcasts with the Experts, an IEEE Future Directions digital studio production. In this episode, we hear from Paul Tilghman, DARPA Program Manager, who has been integral in a 3-year-long Spectrum Collaboration Challenge that attempts to answer the question, do we still need the FCC? DARPA, the United States Defense Advanced Research Projects Agency, gamified a system to create dynamic spectrum sharing through the creation of software-defined radios using the power of artificial intelligence and collaborative autonomy to navigate, share, and optimize wireless spectrum in a testbed called Colosseum, and invited the world to compete. The live championship event takes place on October 23rd at Mobile World Congress, Los Angeles, and will be streamed live.
You know, the background for the Spectrum Collaboration Challenge really comes from sort of two key observations. The first is that, by and large, our wireless world works today because of the FCC, because we have a governmental body that's out there sort of protecting radios from themselves, if you will, making sure that each radio system has its own unique home in the spectrum. But really the flip side of that story is that we're increasingly becoming a wireless society. If you look at how much data travels through the internet wirelessly, it's growing at a compound rate, 50% year over year. And so then you multiply that by things like the arrival of 5G, and it's sort of triggered this spectrum land grab, if you will. And each generation of commercial wireless has required more spectrum than the generation before it, but we've really hit an inflection point where there's really a dwindling amount of spectrum that can be easily auctioned off and licensed in a traditional fashion. And that means that we increasingly have to look at sort of more complex arrangements where one or more radio systems can share the spectrum. And when DARPA looks at this problem, you know, we like to try and forecast out not what will the world look like in 1 year or 2 years, but we like to try and look out and say, well, what about 10 years or 15 or maybe even 20 years out in the future? And really, the Spectrum Collaboration Challenge, or SC2, tries to ask the most challenging question in wireless, which is, do we still need the FCC? Can we actually build a new breed of radios that is smart enough, nimble enough, and the unique part of the Spectrum Collaboration Challenge, that radios that collaborate, can we build this new breed of radio systems so that we no longer require spectrum allocations? Can radio systems be smart enough, all on their own, to learn how to navigate the spectrum? So we find ourselves really in the midst of an AI revolution really taking place over the last decade. And so we find AI doing things like driving cars on our streets. And I think it's reasonable to ask, well, can AI also drive our radios, if you will, around the spectrum? Now, in seeking to sort of ask that question, do we still need the FCC, but do this as a competition, one of your first challenges is, well, where does the competition run, right? Where do these radios exist that are going to try and challenge the norms of how we use spectrum? And we recognized pretty quickly that in order to really put this new breed of radio through their paces, you're going to need to put them in a wide variety, a wide array of different environments and different conditions. Now, to do that in the real physical world is challenging logistically, right? You've got radios, you have to physically move them in space. That means maybe putting them on cars and having people drive those cars. And it's also challenging from a fairness perspective. If I were to take a new radio designed by one of the competing teams in this competition and evaluate it under a certain set of conditions, I want to be able to also evaluate another radio under exactly the same conditions. And so to do this, really, one of the first things we realized we had to do to make this challenge a reality was build a new type of wireless testbed, one that we call Colosseum. And at its core, the way you can think of Colosseum is a large wireless emulator where we take real radios, software-defined radios in this case, but we take real hardware radios and we connect them to something that's called a channel emulator. And the job of that channel emulator is to make those radios believe that they're out in the real physical world. And that lets us create a very replicable, very repeatable wireless environment that we can use as the basis of running this competition. The Spectrum Collaboration Challenge launched back in 2016. Really, what we did at that time is we put an open call out to wireless innovators around the world, and we asked really this software-defined radio community to put on a new hat, as it were. So we asked a community of radio engineers that are good at writing software and good at making software-defined radios sort of bend to their whim. We asked them to put on a new hat. We said, well, now we're going to ask you to also be AI experts and figure out how to blend autonomy with software-defined radios. And in order to actually give these competing teams something to do, we needed to really create a set of rules that form the basis for how you gamify the spectrum. How do you take the idea of sharing spectrum autonomously and turn it into something that can be the backstop of a competition, turn it into a game? And so what we did is we came up with a game that works roughly like this. We take up to 5 radio designs. This is 5 radio networks built by the competing teams in the competition. We take those 5 radio designs, we put them into a synthetic environment that we generate in Colosseum. And beyond that, we give them access to the exact same set of frequencies, and we put them in the same geographic area. Then we give them really one objective, which is to maximize the total, we could think of it as utility, or you might describe it as maximize the total number of wireless applications that we can figure out how to cram into that shared spectrum. Now, there's no rules to how the spectrum is used. There's no preconceived notion that one team should get more spectrum than another, or that certain radio networks should be given certain parts of the frequency band. There's not even really a sense of how to establish an equitable division of wireless resources. Instead, the teams have to rely on their autonomous decision engines working collaboratively with each other to figure out what the rules of the road, what the rules of the spectrum are in real time, which is in the current environment that the radio finds itself, sharing spectrum with these other radio designs, how best to optimize the spectrum under these set of conditions. Now, what makes this really challenging is how little information these radios have. The radio networks don't understand what physical geography they're going to be operating in. They don't understand what the waveforms are that the other radio networks they're sharing spectrum with are using. They don't understand how the other radio networks divide up time and frequency and space. And maybe most challenging, they don't understand how the other radio networks make decision engines, which leaves a lot of open questions that all need to be solved in real time. But if we're successful here, what we'll eventually find is we'll find sort of a new breed of autonomy, a new breed of AI that's able to work together as an ensemble and share the spectrum without having to require the protection of today's spectrum licensing mechanisms. It's a really interesting point when you think about, let's even go back to the name of the competition itself, right? It's called the Spectrum Collaboration Challenge. All right, the last two words are almost oxymoronic in and of themselves, right? We have a challenge, a competition that is collaborative. And so I described the fact that in any one match in our competition, we take 5 competing radio designs, we put them in the same environment, and we ask them to figure out what the rules of the road are. We figure out how to share the spectrum. In that one instant, these 5 competing radio designs are actually, we could think of them as competimates. They're both competing, but at that point in time, they're really peers trying to figure out how to share the spectrum. So they're collaborators. The way that this really turns into a competition is that our tournament is structured as a very large round-robin competition. And so we run hundreds of matches where we pair up different radio networks together with each other. And the idea is that match after match after match after match, if your radio design can figure out how to share the spectrum best, regardless of the other radios that it's paired up with, regardless of the other radio designs it has to share the spectrum with, then actually your decision-making engine and your other radio characteristics really are the best. And that's ultimately what we're looking for. This is, the end of the day, you know, we could think about a radio competition as it could be a competition about brawn, right? Like the physical layer, the waveform that the radio uses to access the spectrum. But our competition is very much the opposite. Our competition is really a competition about brains, right? How do you intelligently navigate the spectrum in order to get the best performance, not just out of your radio, but really out of all of the radios that have to share the spectrum simultaneously? Whenever you set out to challenge a paradigm, and especially, you know, a century-old paradigm like we have in how we manage the wireless spectrum, you really need to start with the idea that you're at a technological inflection point. And there are really 2 technology advances that we saw, and we thought, okay, now is the time to ask this question. Now is the time to challenge the norm. And the 2 big shifts that we saw at DARPA were, one, that software-defined radios had reached a point of relative maturity where you could, on a software-defined radio, you could actually run wireless protocols that achieve levels of performance that hardware ASICs or mimics, you know, silicon-based radio protocols were able to achieve, right? So part one is that the software-defined radio really is, for this competition, lowers the barrier to entry so that anybody can really take part in this competition, right? So we said, okay, software-defined radios have now hit the point where they're mature enough, they're advanced enough that we can actually look at these as being able to execute a relatively sophisticated radio protocol. The other major inflection point is where we find ourselves in artificial intelligence today. And right, it's no secret that we've gone from a world where AI has always been part of computing. You know, ever since the dawn of computing, there's always been some element of using computers to achieve a level of autonomy. But clearly we're in a new era. You know, Siri is in everybody's pocket, or Amazon Alexa or Google Home in your home or apartment. AI is becoming pervasive and it's around us everywhere. And we said, we actually think that AI is now at the point where it's really ready to tackle a challenging domain like the wireless spectrum. But we thought that there's actually still one innovation, one step further that really needs to be achieved in order to be successful in the spectrum collaboration challenge. And that is the shift from what we call isolated autonomy to ensemble autonomy. Most of the examples of AI that we can think of when we think of how AI permeates our life, or even if we think of sort of headline news breaking breakthroughs in AI. So IBM's Deep Blue beating a grandmaster in chess. Google's AlphaGo system beating a grandmaster in Go. IBM Watson beating Ken Jennings on Jeopardy, right? Every single one of these is an example of an isolated autonomous system, right? It's that computer versus a human. When we think about the world of spectrum sharing, there's no versus, right? We need to take the versus out, and it really is now about collaboration, which means that we're not asking for an individual radio system or radio network to be autonomous. We're asking for multiple autonomous radio systems to determine how they work together. And that actually really elevates the world of artificial intelligence, one step beyond generally where we find it today. The competition, now in its third year, has gone through several different growth spurts. It's changed over each year of the competition. In our first year, the way that I really like to think about the first year of competition was really getting our feet under us. And the analogy that one might think about is comparing this competition to, let's say, the original DARPA Grand Challenge, right? Imagine in the original DARPA Grand Challenge, if rather than going to the dealer and buying a car and then starting to equip it with autonomy, what if you had to build the car yourself? That was effectively the first year of the Spectrum Collaboration Challenge, right? Year one, each of these teams really had to focus not necessarily on the key objective of the competition itself, the autonomy. Instead, we had to get our feet firmly planted and create radio systems from scratch. So we gave each team the necessary materials, if you will. We gave them software-defined radios, but they had to write the software that made that radio actually do something useful. So year one was really all about building our car, if you will, right? Building a radio system that has enough, we could use the word knobs or degrees of freedom, has enough of a control surface that then in the future we'd be able to marry it up with artificial intelligence. Year two is really where I think we saw our first glimmer of a breakthrough. In the competition that concluded our second year, the tournament that concluded our second year, we challenged the teams and said, in order for you to win any prizes in this second year, you've got to demonstrate that your radio system can beat the status quo. Right? So the status quo is we take the spectrum. In our competition, we have 5 radio teams trying to share the spectrum at once. So if you've got no other information, what do? Break the spectrum into 5 pieces. Right? Everyone gets an equal allocation of the spectrum. And so we said, all right, what we're going to do is we're going to divide the spectrum into fifths. We're then going to measure how well the 5 radio teams do when we divide the world into 5 parts. And then we're going to measure how well the radio teams do when we throw out the typical playbook, when we throw out the usual ways of managing spectrum. And now we're going to turn the keys over to the autonomy. And we're going to say, can you do better? And at the end of that year, honestly, there was trepidation. We were worried we might not award maybe more than 1 or 2 prizes. And what we found was actually that 6 of our teams right out of the gate were able to demonstrate that they could beat the status quo. We allowed a little bit more time, and then 4 more of our teams 3 weeks later were able to demonstrate that they too could hit that same milestone. And so year 2 really was a very interesting breakthrough, because it was that first time that we really felt that the kind of autonomy these teams were pursuing might really have a chance of demonstrating that this new paradigm, this shift in thinking, was potentially going to really create a new wireless world. Now, as we're geared up here for the third and final year of our competition, I'll tell you what's actually most satisfying is one of the reasons why we ran this as a competition in the first place. Back in 2016, we thought, well, how do you tackle this idea of making a decision engine? How do you tackle building an autonomy that can traverse the wireless world? And as we sat down and whiteboarded, we kept coming up with, several different AI-derived techniques that could potentially be valuable. And so one really good reason to run a competition is because the solution space is potentially large, and you want to explore many corners of the solution space and see which ones actually work out. And I can tell you that now, as we are on the precipice here of the finale of this competition, we've surveyed our competing field, and what we found is that everyone has approached the decision engine in a slightly different way. So we have some teams that are using more traditional autonomy approaches, using expert systems, so think if, then, else types of rules. We have other teams that have approached the decision-making problem as a mathematical optimization. So they've tried to form a mathematical framework that they can then use numerical methods to solve on the fly in real time. We have yet other teams that have really embraced more of the current second wave of artificial intelligence and are using things like neural networks, deep learning, and reinforcement learning. And then what's really interesting is that we have teams that are really a mix of all of the above. So we have, as example, we have teams that are trying to use expert systems as a way to constrain what other AI-based algorithms have to do, right? And so what's really interesting there is that the more general you allow your artificial intelligence system to be, the more data you need to give it in order to teach it how to do something that's effective. If you have a field like trying to understand objects and natural images, and you've got the dearth of images on the internet, this is a really good approach. If you have something like trying to control a wireless radio, where trying to accumulate a significant amount of data is more challenging, then really what you want to do is you want to try and limit how much you're asking each AI subsystem to be able to do or to learn. And so you want to hybridize the physics of, let's say, the way radio waves propagate with more challenging areas that are really fit for AI to do. So really excited as we get ready for this final championship event that we have such a broad array of autonomy approaches. There's two really hard parts to making a public finale for a competition that takes place in the wireless spectrum. The first is really about how you anoint a winner, and the second is about how you present it to an audience. Owing to the first challenge, how do you actually choose a winner? Our goal is to be very objective and really remove as many subjective elements as we can. And so the rules of the competition establish a scoring strategy. And the way to think about it is each radio team gets points for the wireless applications they're able to deliver. And we have wireless applications that have different points awarded for different degrees of complexity. So, for example, sending a simple SMS text message, once a second is worth a point. Getting a voice over IP call successfully delivered is worth 4 points, and streaming a wireless video may be worth something like 10 points. So the more challenging the class of application, the harder its demands in the spectrum, the more points we award. And so by doing this, we've created really a very objective framework where we're judging teams on the ability to share the spectrum and still successfully deliver wireless traffic. And so that really takes care of area one. So we check that box. We've got an objective score to help us find the winner throughout this large round-robin tournament. Now, the second part is turning this into a presentation for an audience, right? A part of DARPA challenges over the years has really become not just tackling the technological problem you sought out to tackle, but also how do you message to the world that advancement when you've made it. And so here in this competition, in the Spectrum Collaboration Challenge, we did a couple things, right? So first, we partnered with GSMA, and they run a conference called Mobile World Congress. And so the key part of this partnership here was we're actually going to have a live finale at Mobile World Congress Los Angeles in 2019 that will really be a chance to highlight what these radios have learned to do over the last 3 years to a live audience. Now, most of you should be thinking to yourselves and asking yourselves the question, how do you actually watch a competition that takes place in a totally invisible medium? And that is a great question. One of the things that we really have as an advantage, because we constructed this Colosseum testbed, is we can record everything. And what that lets us do is we actually have hired a game company, a visualization company, to help us make, on top of a game engine, a way of visualizing the competition. So we can see the spectrum in 3 dimensions. We can actually highlight the spectrum according to where transmissions are successful and where they're failing, and which teams are being successful and which teams are maybe encountering interference. We have all of those capabilities because we've built this visualization engine alongside the competition for the last 3 years. So now here we find ourselves, and we're ready for the finale. We've got 10 teams ready to compete in the finale. We have a visualization engine ready to show the audience, and we have a live finale event at Mobile World Congress Los Angeles. We started back in 2016 with 30 plus teams. I want to say 32, maybe 33 teams. And one of the really interesting things about competitions is that you get competitors that maybe wouldn't normally work with a DARPA. And so what we did is, in addition to the traditional way that DARPA asks for companies and organizations to become performers on our research projects, where we issue a solicitation and people write proposals, and then we select the best proposals from among those that we receive. In addition to that normal approach, we also opened up the competition to the world. And we said, look, if you can show us that you have what it takes, we'll let you into this competition. You don't need to actually write a proposal at all. And so we came up with 3 technical hurdles that you had to pass to show you knew how to participate in this competition. And that then left us with 30 plus teams, right? A lot more competitors than you'd have in a normal DARPA program. Now, throughout the last 2 phases, we've at each of our tournament events, we have given awards to some teams, and then teams that didn't make the award cutoff didn't receive any awards, obviously. And that over time has slowly sort of shrunk down the competing teams to where we find ourselves today, where we have the 10 best teams, the 10 finalists remaining in this competition. When you look into the backgrounds of those 10 teams, what you find is every single one of those teams has software-defined radio expertise really as their sort of core tenet. But many of the teams have brought an artificial intelligence expert into the fray, or many of those teams have actually sort of taught themselves the modern world of AI as part of this competition. The teams come from a relatively diverse set of backgrounds. So we've got a number of university teams that are competing here in the final 10. We also have a number of teams that are really small fledgling enterprises, hoping that the win at Spectrum Collaboration Challenge finale at Mobile World Congress will really elevate their profile, but also use the winnings as a way to take what they've done, start a company, and really further develop their technology. We also even have, believe it or not, we actually have a couple teams that only have 1 or 2 members on the teams, and they've hung in here the whole competition, and it's amazing to see them hit the finale. And in just a little bit of time here, we're going to find out which of these teams really had the successful formula for combining autonomy with the wireless spectrum. After the competition's over, we can sort of look at the previous DARPA grand challenges and, prototype what's happened after each DARPA grand challenge has happened. And generally, a grand challenge isn't necessarily about the technology at the end of the grand challenge. It's really about proving that a new paradigm is possible. And then typically, DARPA steps back and lets the broader research community take those ideas and mature them, right? And let's look at the original DARPA Grand Challenge as an example. It's been well over a decade since that original Grand Challenge happened, and that the Grand Challenge was really proof in the pudding that that we had sort of recognized and realized this pivot point in technology. But it's taken another decade and a half of private research in order to get that technology to the point where it's potentially viable out in the real world. I don't know if the hill we have to climb, so to speak, in the spectrum is exactly as long, but certainly the pattern is applicable. We should expect that after the challenge is done, we've showcased a really different way of thinking about the spectrum. Now, I kicked this off by saying this competition is about asking the question, do we really still need the FCC? The answer, even if the challenge proves that these radios are smart enough that they don't require spectrum allocations, we still have hundreds of thousands of radios that absolutely need and require spectrum to be managed in its traditional ways. But what this will give us the opportunity to is to really lobby potentially for a small ecosystem in the spectrum that is managed in a different way. And so really the next decade of following the competition is going to be maturing this technology and starting to apply it to very specific parts of the wireless ecosystem, but also addressing the policy implications that come along with dynamic spectrum access, but dynamic spectrum sharing. We still don't have an appropriate policy framework that really knows how to vet that radios that dynamically use the spectrum are operating within nominal bounds, and we don't have policies that would constrain them to particular regions of the spectrum. And so there's still lots of work to do after this competition is over. But I think our top 10 competitors are really up to the challenge of taking this technology the rest of the way forward. At the conclusion of the Spectrum Collaboration Challenge championship event, we're going to be awarding a $2 million prize to the first place team, a $1 million prize to the second place team, and a $750,000 consolation prize to the third place team. So there's significant money on the line here, almost $4 million. And really the hope with those funds is that we really expect the teams to take that money and reinvest it in the technology and use that as a way to sort of further their enterprise. And so, will these teams actually, continue to be involved in this technology area after the competition? Obviously, we hope so, and we hope that we're encouraging them to do so by giving them a public event where they can demonstrate that they are the best in the world at dynamic spectrum sharing, and giving them enough of a pocketbook to start their enterprise and really make waves and move this technology forward. So we absolutely expect these top teams to continue forward and become thought leaders in this area over the years to come. I think if we look at what's happened generation over generation in commercial cellular, so we've got a roughly a 10-year cadence where we go from first generation to second to third to fourth and now to fifth. I think increasingly we no longer have these sort of hard generational boundaries. It's sort of more fluid, but every generation has had sort of a charter, right? There's 4G, for example, was all about taking us from wireless connectivity that really represented voice to wireless connectivity that really represented data, connectivity to the internet. But as we maybe think and prognosticate, right? So what comes after 5G, or maybe a better way to phrase it is, what does 5G become in the future? Obviously, I think spectrum sharing has a whole lot to do with it, and that's really the basis of this competition. But maybe if we extend our thinking more broadly, to me, I think 5G is really about establishing data pathways to acquire large amounts of data to enable AI and autonomy. I think 6G will be really all about the wireless ecosystem embracing AI and autonomy itself. So we've already talked about one viable avenue, right? Using AI and autonomy as a way to navigate the wireless spectrum. But a couple other examples come to mind. 5G has moved us, or is moving us maybe, firmly into the millimeter wave. In the millimeter wave, we still don't have good propagation models. That's an area that would be, if you look at the history of how we have good propagation models, or maybe good enough propagation models at traditional frequencies below 6 gigahertz, it really was by collecting lots of data and then using humans to analyze it. And so I think using AI to derive propagation models for millimeter wave frequencies is something that is going to happen, over the next few years. I think another thing to really think about is extending the kind of spectrum sharing we're talking about at traditional wireless frequencies, lower frequencies, and then looking at the millimeter wave and asking, well, how does spectrum sharing work in the millimeter wave? And, because of the wavelength and because of the apertures that are being created in millimeter wave, the spatial dimension really ends up being opened up. However, if you look at most technologies that are starting to come to market in millimeter wave, like 28 gigahertz now, the arrays are actually highly constrained. Not in reality, but the way the vendors have designed them, they've really taken a lot of the degrees of freedom off the table. And I think that, again, using AI to really exploit the really high dimensionality that, spatial dimensionality that is, that these new millimeter arrays will afford us, is another area. And then maybe last, but, maybe sort of overarching and somewhat obvious, is that we should really expect AI to start to take control of the wireless networks themselves. A modern wireless protocol has thousands of control knobs, right? It's got thousands of set points, many of which are set by, network engineers and designers today. But as these protocols become ever more complex, the ability to know precisely how to set all those controls for any particular installation, or the idea that those controls actually can be static and not have to change as a function of time or load or operating condition or environment, is simply not true. And so I really think that 6G is going to be the coming of AI to the wireless world, and it's going to come on a variety of fronts, including not just how to use the spectrum we have, but also how to configure the radio systems that operate in it. So we're right here. We've gotten to the end of the Spectrum Collaboration Challenge. Our live finale event is Wednesday, October 23rd at Mobile World Congress, Los Angeles. So if you already happen to be attending Mobile World Congress, that's great. You can find us on the keynote stage in the afternoon of the 23rd. If you are in the Los Angeles area and you want to attend, that event on Wednesday afternoon is open to the public. And if generally you're really interested in how autonomous radios are going to navigate the spectrum, but you're not in the greater LA area or not on the West Coast, you can tune into our website, spectrumcollaborationchallenge.com. And on October 23rd, that website will actually carry our live stream of the finale event. So you'll get to find out in real time which of these 10 teams is taking home the final $2 million grand prize purse.
Thank you for listening to this edition of the IEEE Future Networks podcast. Discover more about the IEEE Future Networks initiative and inquire about participating in this effort by visiting our web portal at futurenetworks.ieee.org.